number 2. And, okay, I hadn't noticed the top of these instructions. These are also more complicated, not complicated problems, but, you know, they ask 3 or 4 questions of each problem. And no calculator allowed here, so we got to do everything manually. Now, question 3 has to do with parametric equations, which we haven't learned yet and will be the very first subject we tackle as soon as we finish the rest of this test, which is not that far. In fact, I think question 6 may either be the last one or there's just one more section. I think it's probably the last one. So then we'll go back and review a little bit of how you do calculus on parametric equations, and then there's 4 or 5 problems that we have skipped that we'll go back and do. So I thought what we would do today is skip 3 and go straight to 4.
Okay.
Hold on, let me get this so you can see it. Okay. So if A basically says differentiate this thing and verify that the answer is the following. Which is kind of a weird way to ask the question. I'm not sure why they do that. I think it probably has to do with the ladder stuff. Why wouldn't they just say find the first derivative? You know what I mean? Why do they say prove that the first derivative is equal to this? You remember how to do implicit differentiation?
One sec here.
Turn my sound up a little bit. My dishwasher is on. I woke up this morning and my refrigerator was off. I just went and bought $200 worth of groceries yesterday. Didn't like the prospects, and then I went out and realized a circuit breaker had gone off in the middle of the night. I popped it back on and everything came back on.
Wow. Well, that's good that that's all right.
Oh, yeah, for sure. Much better that than a broken refrigerator that was going to cause me to lose a couple $100 worth of food. I guess I could always go out and buy ice and put it in there.
So we got y squared plus 2x.
So how do we get dy dx?
Okay. Well, let's see. I think you got to get the x terms and the y terms on this. Oh, but you can't because there's an x, y.
Exactly. In other words, we cannot easily solve this for y.
Mm-hmm.
That's why we have to use implicit differentiation as opposed to explicit. If you have an equation y is some function of x only, then you can explicitly differentiate it. But when you have a function that is a combination of y's, x's that can't really be separated and solved for y, you can't do it that way. You have to do it implicitly. Basically is applying the chain rule. When I do y squared, you'll remember. Okay?
2y over dy dx?
Yeah, in other words, you differentiate y, and then you have to follow it with a dy dx because it's not an x. The only terms you don't have to follow with dy dx is when you run into an x variable. And you could say, I'm going to follow that with a dx dx, but dx dx is always 1, so we don't write it. Okay, so let's go through this thing term by term and differentiate it like this.
Okay, so then the next one would just be 2.
Plus 2. Mm-hmm.
Yeah, plus 2, and then equals. Okay, And we're doing dy dx. Okay, so this would be
2x.
Oh, 2x. I'm sorry. Yeah,
Okay.
2x.
Uh-huh.
And, so then the next one would be, okay, it would be 2y dy dx. Is that right?
Hold on a moment. The reason I always have trouble with the product rule is because I never know which way the student's doing it, since it can be done either way. In other words, you can do this times the derivative of this as the first term, or you can do vice versa. So what did you say this first term would be?
Okay.
In other words, you have to apply the product rule to that.
Okay, so, well then you'd have 2, if you do it according, okay, I was thinking 2y.
Let me think for a moment. Okay, so you took the derivative of this times that, okay. Now we need the reverse.
So it's 2 times y there, and then plus 2x times y dy dx.
Actually, just times dy dx. In other words, this second term, we need to take the derivative of y, which is 1 dy dx.
Okay, yeah, right. I was something. So it's 2x times just 1 dy dx?
Yes. In other words, the first part of this equation is the derivative of 2x times y. The second part that's added is the 2x times the derivative of y. Well, there's the 2x, and the derivative of y is 1 times dy dx. Just not to lose track of this problem, we'll get back to this, but let's look at a case of explicit differentiation, and you can actually implicitly differentiate this. If I implicitly differentiate both sides, well, the left side is 1 times dy dx. The right side is 2x times dx dx. Well, I don't need the 1, and I don't need that. So that's explicit differentiation, which is the same as implicit differentiation in essence, is what I'm saying.
We're not differentiating both sides with dy dx, or we are?
We are. In other words, I just differentiated that implicitly.
Okay.
I differentiated the left side, and then I differentiated the right side. And I got that. It turns out that that looks exactly like explicit differentiation for that particular problem. In other words, if I said to you, here's the function, y equal x squared, what is dy dx, this is the next thing you would write. dy dx is 2x.
Yeah, right.
Okay.
So let's say we did both sides with respect to z, okay? That would be just
Then it would be dy dz. And over here it would be 2x dz. In other words, you can differentiate with respect to a variable that is not in your function.
Yeah, as long as you put the name of the variable in the name of the numerator and then the other in the denominator.
This is one reason that this notation is so much better than y prime. Y prime doesn't tell you what you're differentiating with respect to. And you get a lot of problems like related rate problems where you need to differentiate the entire equation with respect to a third variable. Okay, so let's go back to this, because our goal is still to solve for dy dx.
So now we would say we're differentiating both sides from the get-go just with respect to x.
Yes.
So we phrase it?
Yes. I'm differentiating both sides with respect to x.
Okay.
So if I had another variable up there, r, when I get to that variable, it's the derivative of r, which is 1 times dr dx. So whenever you run into a variable that is not x, you have to follow it with the differential of that variable with respect to x.
Okay, okay, I think I'm okay. All right, and then, okay, so then we have 1, which that would go out, I guess, regardless of what it is.
Right, that disappears.
So then we're left with that. Okay, so then you would have to, I guess you'd have to, you want to get dy dx on one side and everything else on the other? Is that the idea?
Yes.
Okay.
Now I can do one thing. What first obvious thing that I can do here? See a bunch of 2's.
Yeah, you could divide by 2.
Yeah, that'll help. It'll just make all of these 1's. I can only do it because every single term had a 2 in it. So might as well do that simplification immediately.
Okay. So
It actually does simplify it considerably.
okay, so then you would have, so y dy dx over x dy dx. No, not, yeah.
Hold on. The next step I can do is get rid of those parentheses. They're not needed. Okay, now we have an algebra problem. Strictly algebra. How do I solve for dy dx?
Well, let's see. You'd have to say y dy dx minus x dy dx.
Okay. In other words, we're going to gather all like terms together.
And then,
The like term being dy dx's.
yeah. Then you have equals to x plus y minus 1.
Okay.
All right. Then you could just say, y minus x dy dx.
Right. In other words, we're going to factor out the dy dx here.
Right.
So y prime times y minus x equals all of this. And then we're going to divide everything by
Wait, how
y.
do we get y prime in there?
I just wrote it because it's shorter than dy dx.
Oh, you just did the same. Okay.
It means the same thing.
Okay.
I ran out of room in my paper there, so I wrote y prime. So dy dx is equal to that, which is what they wanted us to prove.
Oh, yeah, right.
Okay. Part B. Determine the points of intersection of the curve with the line y equal 2 and find the slope of the tangent line to the curve at the point with the positive x-coordinate. So I'm going to erase all of this because we don't need that anymore, especially since we're looking at the answer there.
Okay.
And I don't want to erase the original function. So how do I answer the first part of that? How do I determine the points of intersection of the curve with the line y equal x, or y equal 2? In other words, what they're saying is if this is some sort of curve like this,
Yeah.
and I put the line y equal 2 in there, where does it intersect?
Okay, so, well, I would think usually you'd have to solve the two systems of equations together, y equals 2 and y equals whatever, but we don't have a y equals whatever for the top one.
Well, that's okay. There's our second equation. As long as we have two equations and two unknowns, then we'll be able to solve it. And that's our second equation is y equal 2. Okay, so now what do I do?
Okay. Well, now we're trying to solve.
We're trying to find the x coordinates of where these things intersect. We'll know the y coordinate. The y coordinate will be 2. So where on the x-axis does it intersect? In other words, if indeed we had a function like that, and we're trying to discover what is the x-coordinate of that, what's the x-coordinate of that, and what's the x-coordinate of that.
The y coordinates are already 2. We try to
Exactly.
We try to eliminate the y terms, I guess. So you'd say maybe y squared equals 4 for the second equation. Would that work?
Well, don't even need to take that. I mean, that works, actually. But really, the essence of solving this is substitution. Let's substitute 2 wherever we see y, and then we'll have an equation in x that we'll be able to solve. So 4 is y squared plus 2x equals x squared plus 2x times 2 plus 1. So now we're down to one equation and one unknown, and we can solve this. It's a quadratic. We would expect 2 solutions. So let's get everything on one side.
Okay, so then we'd have x squared, minus, or plus 2x, and then minus 3 equals 0?
Yeah.
Okay, so then a is, for the quadratic, a is 1.
This is actually, you can factor this pretty easy.
Oh, what? Yeah.
I mean, you could use the quadratic, and I'm not sure you're wrong in doing so. You're good enough at it.
Okay, so x, let's see.
X plus 3 times x minus 1.
Yeah, okay. Yeah, right. Okay.
In fact, I'm constantly wondering what the correct thing to do is when you are given a quadratic to solve. Do you waste time or spend time trying to factor it, or do you immediately go into the quadratic formula?
I wonder if there's any way to determine right off to do,
analyzing the determinant, which is the b squared minus 4ac part, might be the way. Because if that gives you a whole number, then it factors. If it doesn't, if it leaves an irrational number, in other words, if this part right here, b squared minus 4ac, does not convert to a whole number, then there's no way it factors.
Oh, I didn't know that. No kidding.
Yeah,
So already
if this were, say, 8, if b squared minus 4ac were 8,
then it could
no,
be,
because the best I can simplify that is square root of 2, and that's irrational. So that's going to require the quadratic formula. And if, like in this situation here, if we analyze, let me just double check my reasoning here, because I hadn't, this is the first time I've actually discovered this. B squared would be 4 minus, or plus 12. So, yeah, square root of 16 converts to a whole number 4. We would expect there to be, that would tell me that it, in fact, does factor. Of course, I've had to do a lot of work to do that. I had to analyze b squared minus 4ac. So it still doesn't exactly answer my question. I mean, that is a litmus test, but I'm not sure that it's necessarily one you want to do. I suppose it kind of comes down to whether you expect it to factor or not. If you're doing a real-life problem, in other words, if we were 2 engineers out trying to fix the sand at a beach, we would not expect a quadratic to factor. Just because the world doesn't come in that neat of a package. I mean, I guess there's a lot of discrete mathematics where it would, but it's only in math class that I think most quadratics factor nicely.
Yeah, I see what you mean.
Okay,
I see what you're saying.
so this tells us that when x is equal to 1 or when x is equal to minus 3, that's the intersection points. So my coordinates of intersection are going to be 1, 2 and minus 3, 2. Those are my 2 points where these two curves will intersect, both the x and the y coordinate. And we want the slope of the tangent line to the curve at that point. How can we get that?
Tangent line to the curve at that point.
In other words, we have...
Oh, is equation A the slope of the tangent line? I mean, that's dy dx, right?
Yeah, yes, exactly.
So we just substitute the x and y's into
You got it. I was just about to help you get to that point, but you got to it before I could draw it. So the slope of the tangent line at this point, slope is x plus y, 1 plus 2 minus 1 all over y minus x, which is 1. So that slope is 2. And they only wanted it at the point with the positive x coordinate. They didn't want it at the other coordinate, which has a negative x coordinate.
All right.
Now, when I first saw this problem, I wondered whether we needed to guard against y minus x being equal to 0. Because if y minus x were equal to 0, in other words, if y were equal to x, that first derivative would be undefined. If we go up and look at this first derivative here, notice that y cannot be equal to x.
Oh, okay, I see what you mean.
And that would be a restriction on the thing. Gee, I wonder what happens when y is equal to x to the derivative. In other words, if whatever this curve looks like, it might be worth graphing this in Wolfram alpha just to satisfy my curiosity about, in other words, if that curve looks like that, the derivative, no, that would be the original function. The original function is some sort of a hyperbolic.
Yeah, that's another thing I need is just to be able to look at the equations and figure out what general shape they, you know,
well, let's look at this equation here.
Okay.
Notice we have a y squared, we have an x squared, we have an x, and we have an xy. This almost fits the equation of an ellipse. And in fact, it would if I take away that xy. If I had just this, y squared plus 2x equal x squared plus 1, that's the equation of an ellipse. I can put that into x minus h squared divided by a squared plus y. Hold on a moment. I jumped the gun a little bit. Y minus k squared equals 1. I can rearrange that thing and figure out how to make that happen. But now I'm realizing I can't. I can put it into x squared minus y squared. This is the equation of a hyperbola. Okay? An ellipse is like this. A hyperbola is like that.
Yeah, right.
Okay? So this would be the equation of a hyperbola.
Okay.
When you find,
Because it's x squared minus y
yes,
squared, and then, but what about the 2x and the 1 and
I can
whatnot?
take
How
care
does
of the
that?
2x by completing the square. In other words, I know k will be 0 because I don't see any other y term. But I'm going to
Okay.
have to put the 2x with the x squared, complete the square, to turn it into an x minus h squared.
Oh, I see.
And that's
Okay.
what we'll do. And in fact, this is a very typical problem. They give you that function and they say, graph that hyperbola. And
And then
you
you
would
have to
have to
complete the
complete the
square.
square, exactly.
Okay.
Okay? Now,
Can we do that real quick, just for a review, just
yeah,
so I
for
can
sure.
remember how to do that?
Sure, that's a good idea.
That'd be
What
great if
we're
we
looking
could.
at, what that xy term means,
Uh-huh.
is that we have a rotated hyperbola. In other words, we don't have,
So it's not.
it's not either horizontal or vertical. It
Okay.
is, whenever you have an xy,
The axes are like rotated.
all of these things are rotated. That's what the existence of the xy means.
Ah, okay.
Okay? And that means that that's how that would graph, is some sort of a rotation of a hyperbola.
Okay.
Now it explains what happens when y is equal to the x to the first derivative. I think it does. The slope of the tangent line would still exist. It would be vertical.
I see.
It
Yeah.
would have to
I
be
got you.
right
Like that.
there, which means that point is where x is equal to y, and the same thing down here when you find that slope vertical. So division by 0 doesn't necessarily, this is why I object a little bit with my Algebra 2 and pre-calc students in using the word undefined. I think infinity is much
It is
better.
vertical, right?
Yeah, because it means something. It doesn't mean that y can't be equal to x. It can. See, my interpretation when I first looked at this was that y can't be equal to x because you can't have division by 0. But you actually can. Because if y is equal to x, that means the first derivative would be infinite. You'd have division by 0, which is infinity. And that merely means the slope is vertical. So this is cool. I'm glad I turned this into a conic section problem because it answered my question. I was sitting there trying to figure out, well, what's going to happen to the first derivative curve when y is equal to x?
So that's why they didn't have to put in the restriction of y can't
Yeah,
be equal to
I
x.
bet it is. Exactly. Because normally they always cover their asses.
Right,
You don't ever see a math problem like that without them covering the impossible. You can't divide by 0.
Huh, yeah, that's true. That's true.
So let's go back and solve this.
Okay.
Okay, we're trying to get that into this format. So I'm going to, nice of them.
Wait, this was still part of B? This was
No, this was merely, I changed the function. I removed the 2xy.
Okay.
So that it was a conic section that we were used to dealing with. That's the next area of math I'd like to cover also, is rotated conic sections.
Okay, sure.
I don't run into it very often, but I've run into it once, maybe twice in 6 years. But it's pretty hard. It's pretty complicated, although not that hard. I think we'll be able to get a handle on it pretty easily.
Okay.
But if we were in conic section pre-calc class, and we were given this, and we had to graph it. In order to graph it, you have to get it into its general format. If I can get it into this format, I know exactly how to graph it. Okay, because I'll know A, I'll know B, I'll know H, and I'll know K. And so I'll be able to draw my box. Remember, to graph a conic section, you need an imaginary box to start with.
Yes.
That comes from A and B, And the diagonals to that box are your asymptotes, and your hyperbola is asymptotic, and draw it very good,
to the box.
Not to the box, but to these diagonals.
Now, can the diagonals cross beyond the box, or they have to exist beyond, I mean, outside of that box?
They're always linear. Yeah, they're linear and they go to infinity.
Okay, do they touch the box, or are they always slightly?
They're always the center, where they cross is the center of the box. In other words,
yeah, I guess I'm saying that can they go beyond the, let's say, right or left-hand boundary of the box, or they must stay outside of that, I thought. Is that right?
Not sure what you're asking. In other words, I would extend that to infinity and that to infinity.
Yeah, I understand that.
Hyperbola is always never going to touch that diagonal. It's always going to get closer and closer as we go to the right on the x-axis.
So if you look at the vertex of the, let's say the right-hand sort of parabola that has the asymptotes or whatever.
Let me erase everything else because all of this is invisible. You don't actually graph the diagonals or the box.
Right.
It's not part of the graph. The graph is the part that's left.
Yeah, I was just asking with the box there, drawn in the dotted lines, does the vertex of those left and right parabola-looking things, do they intersect the box, or are they outside?
In other words, if I had to draw the box here, it would be like that.
Do they touch?
Yes, it's tangent. That's the major vertex, and that's the major vertex.
Okay, I got it.
And this is actually, the horizontal line here is the major transversal line. And that's always where A is measured. In other words, I haven't drawn it very correct here, but that distance is A, from here to here. This distance is B, from there to there. If it's a vertical,
then would it be y something minus x, like that?
I'm sorry, what?
Then would the equation be y minus k minus x minus, like that?
In other words, if the x has the positive sign, it's a horizontal hyperbola. If it's y squared minus x squared, it's a vertical hyperbola. And A always goes on the major axis. In other words, so A is always measured halfway between your two major vertices is A.
Okay, I see.
No matter where it is. In other words, I've drawn it at the origin. But regardless of where this would be drawn, A is going to be half of the distance between the two major vertices.
Okay. And then the other thing, just completing the square.
All right, let's go through it.
Yeah.
We know this is a horizontal one. So we're going to put all of our x terms together. I'm going to move everything to the right. Ooh, interesting. Let's see. We got x squared minus 2x minus y squared equals minus 1. Right?
That's x squared minus 2x minus y squared. I think it would, okay.
Yeah, I moved that 1 to the other side.
I'm sorry, I got you.
My final version, in other words, the general format, has a 1 over there, so I'm going to need to do something to turn that into a 1. But
yeah, that's what you mean.
Yeah, now I say a problem. And it might be because I made this up. But how do we complete the square over here?
Okay, so as far as I remember, you divide that middle term by by 2, and then you square it?
Yeah. So I'm going to add 1.
Okay, add 1 there, and then you got to add 1 to the other side?
That's where the problem's going to come in. Yeah. Now that
that
other side's going to be 0, and I don't know what to do with that.
Yeah.
Well, if it was any number, in other words, now I can rewrite the left side that way, and
then
y squared, and
it'd be 0. But if it was some other number than 0, you just divide by
0, I can turn it into 1. If it's, say, 10, then I can divide every term by 10, and I'll get my A, I'll get my B, and I'll have 1 on the right side. If it was 1/4 or minus 1, I could turn it into a 1. The only one I don't know how to turn into a 1 is 0.
Yeah, that's not even possible.
Well, it might be, and it might be because I took this function and just removed the 2xy. I might have created one. Let's go into Wolfram Alpha and see what this thing looks like.
Okay.
Just out of curiosity. Oh, I forgot. If I don't do this first. Hold on. If I immediately open up Google Chrome, it opens up 6 spy windows up top. Whereas if I open up this first, and now I go to Google Chrome, it only opens up that. So I always have to initiate my Google Chrome by doing that, and then I'll turn that one off. Now I'm good to go. Let's see. Y squared plus 2x equals x squared plus 1. Y squared plus 2x equals x squared plus 1. Oops.
I think you had a 6 there.
Yeah, see it. Okay. So, what do we expect to get before I hit the enter key?
Well, hyperbola, I thought, isn't it?
Well, maybe, maybe not. The fact that I got a 0 over there bothers me. I'm trying to figure out what the consequences of that are going to be.
Oh, I see what you mean.
In other words, before I hit enter there, I'm kind of curious. I could add 1 to both sides. Why does that not work?
Yeah.
That does work.
Let's see. Yeah, if you add 1 to both sides.
Then I get x. Ooh, that does present problems, though, because I don't know how to handle that. In other words, I can no longer turn that into y minus something squared, or y plus something squared. There is no y plus or minus k squared that will equal y squared plus 1.
So yeah, you're in the jam there, I guess, too.
Yeah, so adding 1 to both sides doesn't work. Division by 0 doesn't turn the right side into 1. I may have just randomly picked something here that is not a hyperbola.
Could you subtract 1 from both sides or something? Would that do anything? Or?
No, I still would be left with the same problem. If I had a minus 1 over there, I wouldn't be able to... Oh, no, hold on a moment. Yeah, see, it's got to be y, in other words, we need to end up with a y plus or minus quantity squared. And regardless of whether this is plus or minus, you end up with another y term there. In other words, I can't do anything with that either. So my guess is that because of that, this is possibly a hyperbola that's rotated, maybe. I don't know, I'm kind of curious. So let me hit enter and see what they do. I didn't get it. What the heck? Oh, here we go. It's a parabola. How is that a parabola? because you have an x squared and a y squared. That's not a parabola. Notice that they did not show us a graph. Which means I must be right that this is not a what is this if they can't graph it? One of these days I'm going to have to pay for the more advanced version of this.
What do they do with the more advanced one?
Oh, they just give you a lot more capabilities. You can do things like zoom in on graphs. In other words, if they would have graphed this, I've been stuck with viewing it in their two modes, and that's it. You know, even on my calculator my manual calculator that I have, I can zoom in, zoom out, find intersection points, stuff like this. This does a lot, but it doesn't do everything. And it would not graph this. So I was correct. This is not a hyperbola. I don't think it's a parabola either. I mean, parabolas are either x squared equals y or x equal y squared.
And these are both squared.
Right, exactly. And when they're both squared, it's either an ellipse or a hyperbola. And when you have an xy term, it turns into a rotated something. And when we get to that chapter, we'll investigate that, because that's what that chapter is all about, is why you end up with an xy term and ellipses and hyperbolas. And in fact, if you take the basic hyperbolic equation, this is one of your 10 elementary functions. Notice what this is. This is xy equals 1.
Ah, yeah.
There's the xy term, and there's the rotated hyperbola.
Yeah, how about that?
How about that?
That's true.
And what's interesting about it is that the rotated hyperbola is a much, much simpler function than the horizontal or the vertical. The horizontal or the vertical hyperbolas have to be in this format up here, which is really complicated.
Yeah.
So some rotations apparently cause all of the complicated terms, the x squared and the y squareds, to disappear, and you end up with just an xy equal 1 as your hyperbola. So I suppose you can't say, well, that's interesting. That means that not all hyperbolas have an x squared and a y squared in them. Only horizontal or vertical ones are guaranteed to do that. Which makes me wonder
What if that
parabola is something like that. In other words, if you have a parabola, except I'll bet you if I do a parabola and I rotate it, I still only have, I may have an xy term, but I bet I don't have both an x and a y squared term. But that'll be in that section also. So that'll be interesting to find out. If this was the case, why didn't Wolfram Alpha graph it for us? If it truly is just a rotated parabola. Now, it could be because I don't have the advanced version. In other words, if I had the upgrade, the professional version of this, maybe they would graph a rotated.
I see.
I'm sure they'd graph my hyperbola, y equal 1 over x. Let's see if they graph that. That's a rotated hyperbola, after all. That's all it is. In other words, do they not graph? No, they do graph it. Well, that'll be something for us to discover. It is curious that they labeled it a parabola. The other one.
And all you did was just eliminate the xy term, right?
From this function here, yeah. In fact, let's graph this function here that they gave us. Ah, shit, I did the same thing again. Hold on a moment. Got to open that. Should just not close it. I'm so sensitive to having more things open than I need. So this function should be a hyperbola that's rotated. And we'll see if they have the ability to graph it or not. Y squared plus 2x equals x squared plus 2xy plus 1. It is. It's a rotated hyperbola.
Yeah, there it is.
Now, interesting that removing the 2xy makes it ungraphable. But that's because when you remove it, you cannot put it into standard format. That's the first hyperbola I've ever come across where you end up with 0 over there, and that presents a big problem.
Yeah, that's a pretty unique case. I'm sure it doesn't happen.
Yeah, no, I mean, I made it up by just accidentally removing that,
Right.
which was the wrong thing to remove. Put any other numbers, put other than a 2 there or other than a 1 there, and you don't end up with that 0 by removing that.
I wonder if there's any, like, convention they could do, like, change to 0 over... No, you couldn't do 0 over 0 because you have to multiply...
Well, I was thinking of that. You could do 0 over 0, but the question is that going to be equal to 1? I suppose you could do 0 over 0 and apply L'Hopital's rule. I don't think so.
Well, you'd have to multiply the other terms by 0 then, I think.
Yeah, you'd have to divide everything by 0.
Yeah.
And so yes, I don't see that. I think when you end up with 0 on that right side, you do not have. Well, it's probably some sort of equivalent of dividing by 0 or something. I don't know. It'll be interesting. We'll solve that question when we do that section on rotated conic sections, which I'm almost anxious to do now. Merely also because rotated conic sections are what the universe is all about. You don't. Everything isn't nice and vertical or horizontal.
Yeah.
You know, when you're analyzing solar systems.
Right.
And it would be kind of fun to get to at least the point where we can actually see how they use these to analyze the movement of the planets in our solar system. That'd be kind of fun.
Yeah.
To understand that. The math of it.
Yeah, that would be nice to know that kind of stuff.
All right, Timur, I will let you go and talk to you next week probably sometime.
Pick it up next time.
Okay.
All right, Dave. Thanks much. Take care.
Bye-bye.